Hello, in this video we will be looking at the Maxwell model that we have already discussed in the previous video. In this video specifically we look at how do we derive the stress strain relations, and we will also solve these equations for few given loading conditions. So, to give an outline of this video, we will start by deriving the stress strain relations of the Maxwell model and then look at solving this equation for given loads such as the creep loads, relaxation load and a constant strain rate. So, let us first start with the stress strain relations for the Maxwell model. So, first we know that the Maxwell model is nothing but spring and damper kept in series. So, this is the representation of it. We have a spring in series with a damper. So, we represent the spring with material constant E modulus and the damper with viscosity nu. Okay. So, to start deriving the stress strain relations, first let us write what are the constitutive equations of these elements, the spring and the damper. So, for the spring, we know that the relation between stress and strain is the Hooke's law. So, the stress in the spring is E times the strain in the spring. Similarly, for damper, the stress in the damper denoted as sigma d is given as viscosity mu times the strain rate in the damper epsilon dot d. Okay. So, these are the constitutive equations for the elements spring and the damper. Now, let us look at how do we get the relations between the applied stresses and the strains, because the applied stresses and strains are at the ends sigma and epsilon. So, first let us look at the equilibrium equation. So, we know that since the spring and the damper are in series, the same stress, the applied stress sigma applied at the ends of this Maxwell element are the same at the spring as well as at the damper. So, we write sigma is equal to sigma s, the stresses in the spring and the stresses in the damper, all three are the same. Now, let us look at the kinematic equation. Kinematic equation meaning how does the displacements look like. The total displacement or the displacement applied at the ends is the sum of the displacements in the spring and the displacement in the damper. So, the strain in the spring denoted as epsilon s plus strain in the damper denoted as epsilon d. So, the sum of these two strains will give the total strain epsilon. So, let us number these equations saying that 1 and 2 are the constitutive equations of the elements, 3 is the equilibrium equation and 4 is the kinematic equation. Okay. So, from equation 4 we get that first let us differentiate both sides with time. So, then we get strain rate is equal to strain rate in the spring plus strain rate in the damper. We do this we look at strain rates because we notice for the damper we already have the strain rate. So, it will be easy to write in terms of the strain rate in damper, and spring we will differentiate on both sides. So, which means we will replace the strain rate in the spring as Once we differentiate both sides of equation 1, we should be able to write what is the strain rate in the spring, which is sigma s dot by E. And strain rate in the damper is readily available, which is simply the stresses in the damper by the viscosity mu. Okay. So, actually we should write from equations 4 as well as we used equations 1 and 2. Okay. Now, let us revoke this equation 3, which says the stresses are same in the spring, in the damper, or overall in the Maxwell model. So, from equation 3, we can write that the left hand side remains the same, the strain rate. We will replace the stresses in the spring with stress in the Maxwell model. So, we will simply write it as sigma dot by E plus sigma by mu. So, this should give us the relations between the stresses and strains in the Maxwell model. But usually in the viscoelastic literature, there is a particular format by which in which we write these equations. We will bring all the stress terms to the left and the strain terms to the right, and whenever we write these quantities, we go in the ascending order of the time derivatives. So, usually this is written as the standard format. The standard format is you start with sigma without a constant, and then there are constant times the first derivative of the stress, constant times the second derivative of stress, plus so on and so forth. And towards the right we have these constant times the strain and constant times the first derivative of the strain, second derivative of the strain, and so on and so forth. So, let us try to bring this the equation we derived into the standard format. So, for that I need to bring the stresses to the left, and since the first term should not be without a fraction, I will multiply the whole equation with viscosity mu. So, this will get me mu by E times sigma dot equals mu times strain rate. So, finally, this is the equation which we will be using for stress strain relations in a Maxwell element. So, here we will also introduce one constant which is mu by E. This mu by E, which is the ratio of viscosity by the modulus, can be represented as relaxation time tau. Later when we go through the video, we will again come back to this relaxation time and see what is the physical interpretation of it, or how do we represent or get it from experimental data. But this is an important terminology which we will be coming back to while solving or using these equations. Okay. So, in this slide we have shown what is the relation between the stress and strain for a Maxwell element, because we have the stress differential and the strain differential. But now let us look at how do we use this equation to get the response from a Maxwell model. We will start with the creep behavior. So, we will start with the Maxwell equation, which is sigma plus mu by E times sigma dot equals mu times epsilon dot, and we said we are applying the creep load. We represent the creep load as sigma t equals sigma naught, which is the initial load applied, times the Heaviside function h of t. So, let us number these equations as equations 1 and 2. So, the idea is now we know what is the creep load or the input, given in terms of stresses, we need to find out what are the strain response. So, for that we will apply the Laplace transforms, but before we apply the Laplace transform, let us first substitute equation 2 into 1. So, substitute equation 2 into equation 1, that should give us sigma. We will replace sigma with sigma naught times h of t plus mu by e times the first derivative or the derivative of this stress will be sigma dot is sigma naught times derivative of the Heaviside function is nothing but the Dirac delta function delta t. So, we will write it as sigma naught times delta t equals mu times epsilon dot. Okay. So, first we will start with the Laplace transform. So, we will apply the Laplace transform on both sides. So, here we need to recall few formulas what we already discussed about Laplace transform. So, we will start by Laplace transform of h of t minus a is 1 by s times e power minus a s. Similarly, Laplace transform for the Dirac delta function delta of t minus a is simply e power minus a s. So, let us substitute these into these equations here. So, for the first term it will be sigma naught times, in this a should be taken as 0. So, it will turn out to be 1 by s plus mu by e sigma naught times for Dirac delta function, since again a equals 0, this will be simply 1 is equal to mu times. So, now let us look at what is the Laplace transform of the strain rate. So, the Laplace transform of a time derivative of a function f of f dash of t, earlier we have shown that it is s times Laplace transform of the function s minus the function at time 0. So, we also need to emphasize that it is 0 minus, which means slightly left to the time t equals 0. So, now let us apply this formula here. So, this should be s times the Laplace of strain minus the strain at slightly less than 0. So, we know one thing, that the load only happened at time t equal to 0. So, anything left to time t equal to 0, there is no stresses nor strains. So, we can ignore this second term. Okay. So, once we ignore that, the next thing to be done is to simplify this equation and write it in terms of strain, because that is the response we are trying to solve for. So, now strain in the transform domain can be written as, so we will move this mu times s to the other side of the equation. So, it should give sigma naught by mu times 1 by s square plus sigma naught by e times 1 by s. Okay. Now, we got it in a expression which is neat enough, and each of these terms on the right hand side we know the direct formulas of inverse Laplace. So, let us apply that. So, we will now apply the inverse Laplace on both sides. So, to the left hand side we will be strain in the time domain is given as sigma naught by mu times what is the Laplace inverse of 1 by s square. So, again from earlier discussions we have seen that the Laplace of time t is given as 1 by s square and the Laplace of a constant is given as 1 by s. So, let us apply this to these equations here. So, inverse of 1 by s square should give us time t, and inverse of 1 by s should give us a constant 1. Okay. So, the way we will write it as is epsilon of t equals, we will pull the common sigma naught and then write the other terms in the equation. So, this should give us T by mu plus 1 by E. So, let us highlight this. This is the response we are looking for the creep load when we were discussing about this Maxwell model. So, for a Maxwell model, when a creep load is applied, the strain is given by this expression here. But let us try to visualize what is this expression by using some plots. So, we said the input is in terms of stress. So, we said the stress remains constant, that is what we define as the creep load. And for the response, let us look at how it varies with time. So, the response here is the x axis is time and the y axis is the strain. So, in this expression, let us substitute what happens at time t equals to 0. At time t equals to 0, epsilon or strain is sigma naught times the first term goes to 0 because the numerator is time and it is 0, and what we are remaining it is with the second term 1 by E. So, as we see, sigma naught remains constant throughout the experiment and E is a constant for the spring. So, which means we have a constant value to start with, and that value is given by sigma naught by E. But now let us look at what happens as the time increases. As the time increases, now we will be looking at this first term. The first term, as we have seen, it is a linear term in terms of time t. So, with time the strain gradually increases, and this slope, the increment is given as sigma naught by mu. Where are we getting that? That is the coefficient we have in the first term. Okay. But let us look at what happens at infinite time. At infinite time, meaning if the time t tends to infinity, then the strain is also infinite, because simply we have t, when t goes to infinity, even this equation or the expression to the right hand side goes to infinity. That is what is represented in this plot. So, we have now seen what is the response, creep response to a Maxwell model. Now, we will use the same kind of formulation to show you how to derive the response for relaxation loads. We will again start with the Maxwell model. Now, when we say the relaxation load, that is given in terms of strain. So, the strain at any time t is given as epsilon naught times the step function h of t. Okay. Now, let us substitute this relaxation function into the Maxwell model. So, let us again give these numbers 1 and 2, we are substituting 2 in equation 1. So, that should give us sigma plus mu by E times sigma dot equals mu times the derivative of the Heaviside function is the Dirac delta function. So, it will be simply epsilon naught times Dirac delta function delta of t. Now, let us apply the Laplace on both sides. So, that should give us sigma of s plus mu by E. Again the Laplace of the first derivative of a function will invoke, that should give us s times sigma of s plus sigma of 0 minus. equals viscosity epsilon dot, and what is the Laplace of a Dirac delta function? We have seen it is simply 1. And again since our loads and the responses start only at time t equal to 0, anything to the left will be 0. So, this term can again be ignored. So, let us simplify this. So, since now we need the response in terms of the stresses, we will put that in the left hand side and move all other terms to the right. So, this should give us mu epsilon naught divided by 1 divided by 1 plus mu by E times S. But the denominator, we should ensure that we can apply the inverse Laplace transform. Now, let us recall the Laplace transform of e power omega s. It is given by 1 by s plus a, which means we need to term this denominator in our equation in a form of s plus constant. So, the way to do it is we will multiply and divide both side both numerator and denominator by E by mu. So, E by mu times mu epsilon naught, and to the denominator it will be E by mu plus S. So, if we cancel those terms, it will be E epsilon naught by S plus E by mu. But if you recall previously we defined the relaxation time tau is given as mu by E, and 1 by tau is of course E by mu. So, let us recall that and replace this E by mu with 1 by tau. Now, once we apply the inverse Laplace, so now we should be getting the stress in the time domain is equals to E epsilon naught times. So, now we need to apply the inverse Laplace transform of 1 by s plus 1 by tau. So, looking at the formula we gave at the bottom, this can be written as e power minus t by tau, because the constant here the a is minus 1 by tau. Okay. So, with this we should be able to write this as e power minus t by tau, which is the relaxation rate. Finally, this expression is the response, the stress response for relaxation load if you are considering the Maxwell model. But now let us look at how this response can be visualized. So, we said the input is with time, the strain is constant at epsilon naught. Now, we are interested in how the stress varies with time. Stress varies with time. So, let us first plug in time t equal to 0 and see what we get for stress. At time t equal to 0, the stresses at time t equal to 0 is E epsilon naught times e power 0. E power 0 is 1. So, what we get is simply E times epsilon naught. Let us also look at what happens when time approaches infinity. So, then the stress is given as again E epsilon naught times e power minus epsilon by tau, which can be written as 1 by e power infinity, which again goes to 0. So, this term goes to 0. So, the overall is 0. So, actually to represent at time t equal to 0, we notice that this value is at E epsilon naught, and as we approach long and long times, or once if we wait for long times, the stress goes to 0. Okay. But there is one more interesting observation we can make from this equation. By plugging in what happens when time t equals the relaxation time given as tau. When time t equals tau, sigma is E epsilon naught times e power minus tau by tau, which is minus 1, which is simply E epsilon naught times 1 by E. So, now if we represent it in the plot, saying that we are looking at tau, which is the relaxation time, the corresponding stress will be E epsilon naught times 1 by E. Okay. So, we know that E has a value of 2.1. So, this 1 by E has a value of 0.37. So, this value is 36.8%. So, why we are stressing about this is, let us say we are testing a polymeric material which behaves like a Maxwell model. We have done the test, which means we to start with we do not know the material properties. We are indeed conducting this test to know the material properties uh, E and viscosity mu. How do we find them? So, once you have a response like this, we said that this is the input and this is the output. So, we know at the output at time t equal to 0, we got some quantity, we named it as E epsilon. So, since you know what is the input, which means what is the initial strain you have given, from your measured initial response of the stress, one should be able to find out E. So, that is step 1. So, then what you do is you look at what is the stress value, which is 36.8% of the initial value. So, then we are looking at 36.8% of initial stress. What is the initial stress? E epsilon naught. So, once you know that, you mark it on the y axis and then trace it to the curve on the point on the curve, and then again if you trace it to the x axis, then you get what is called as the relaxation time tau. So, from this you get what is the relaxation time tau. So, once you find tau, it should be easy for us to find what is the viscosity mu, because viscosity by E we said is tau and viscosity is simply E times the relaxation time tau. So, in this way, once I have the input plot and the output plot, I should be able to find out first the value of E from the instantaneous response and the value of the relaxation time from this 36.8% the fraction of the initial value. And once I know the modulus and the relaxation time, I should also be able to find out what is the viscosity of this material. Okay. So, what we have seen in this slide is we derived what is the stress response when a Maxwell model is applied a relaxation load. So, for the Maxwell model we applied the relaxation load. Finally, what we will do is we are done with the creep loads and the relaxation loads, but sometimes it is not just the creep and the relaxation loads, there are many other loads people use to conduct experiments or to characterize viscoelastic materials. So, in that motivation, let us also look at what is the response under constant strain loading. So, we are again talking about Maxwell. So, let us again write the equation. And we said now we are interested to look what is the response under constant strain load. Okay. So, let us represent it using a curve. So, we say that this is with time the strain responds linearly, constant strain rate, and this strain rate we are representing with a constant r. So, we are trying to find what is the stress response for a given load like this constant strain. So, how do we write it in terms of equation? So, this constant strain can be written as epsilon at any time is simply r times time t. So, for now we will ignore the step function because then it will make our derivations easy, but otherwise one can always do it in a more rigorous fashion, but here because of the time let us take a simple approach. Okay. So, now we say we will substitute this equation 2 into equation 1, which is the Maxwell equation. So, that should give sigma plus mu by E sigma dot equals mu times the derivative of the strain is nothing but r. Okay. So, it will be mu r. Now, let us apply the Laplace transform on both sides. So, this should be sigma of s plus mu by E, again we will write it as s times sigma of s, again we will ignore the sigma 0 minus since it will be 0 anyway, which will be equal to mu r. So, which will be mu r times 1 by s because the Laplace of a constant is 1 by s. So, now let us simplify bringing the sigma of s to the left hand side of the equation and the rest to the right hand side. It will be mu r by s times 1 plus mu by E s. Okay. Again we want to write this denominator times as s plus constant. So, we will do that by multiplying the numerator and denominator by E by mu. So, E by mu times mu r, where both of these will be cancelled, by s times s plus E by mu. Okay. Now, we need to find a way where we can do the inverse Laplace transform. So, currently it is not possible because the denominator is s times s plus a. We need to further simplify it. One trick to simplify it is first to in the numerator let us try to bring these terms of s plus a or s plus E by mu. The way to do it is ER, we will say that we need to get this E by mu in the numerator. So, for that let us pre-multiply this again by mu by E. Again these two will cancel out, and once we do that I will add n s and subtract n s, which should not change this constant. So, once I write it in this fashion it allows further simplification, which we will just see. Okay. So, now if I only consider these first two terms E by mu plus s, it should give me as mu r. So, in the numerator and denominator we have this s plus E by mu, they both cancel out and what is remaining is 1 by s. And now once we consider the remaining this simple minus s, it will be s and s will be cancelled out in the numerator and denominator, and what is left out is 1 by s plus again E by mu I will write it as 1 by tau. What is tau? The relaxation time. So, once I have it in this fashion, it will be easy for me to apply the inverse Laplace transform, because we have standard formulas for this. So, now once we apply the inverse Laplace transform, so we get stress in the time domain is mu r times what is the Laplace inverse Laplace of 1 by s? It is simply 1 minus. So, we know that the inverse Laplace transform of 1 by s plus a is simply e power minus t by tau. Okay. So, this should give the final response for constant strain load for a Maxwell model. Again, now let us see how do we plot the response. So, for that let us substitute time t equal to 0 in this equation. It should give time mu r times 1 minus e power 0, which is 1. So, which means the answer is 0 instantaneously, it starts from the origin. But when time t approaches infinity, then we get it as mu r times 1 minus 1 by e power t by tau. Since the denominator here goes to infinity, this term approaches 0, and finally we get it is simply mu times r. So, this should be starting from 0, and at time t equal to infinity it approaches a constant, and that constant is given as mu r. So, in this slide we have seen for a Maxwell model, when you apply a constant strain load, then the stress response instantaneously it is 0, and finally towards the end it reaches a constant given as mu r. So, to summarize what we have discussed in this video, we started by showing you how to derive the stress strain relations for Maxwell model, and using that stress strain relation we have solved it for 3 different loads. We first showed you the response for the creep load, then showed you the response for the relaxation load, and finally in this slide we showed you the response for the constant strain loading. So, with this we conclude this lecture, and in the next lecture we will look at the Kelvin model.